Right now, 24 billion kilometers from Earth, a small piece of human engineering is drifting through the absolute darkness of deep space, completely alone. What makes that distance staggering is when this machine was built. It launched in 1977. We sent this craft into the void relying on the computing power of magnetic tape and massive server blocks, before GPS or smartphones existed. The reason we launched with that technology, instead of waiting for better computers, comes down to a mathematical discovery by NASA engineer Gary Flandreau. He realized that Earth, Jupiter, Saturn, Uranus, and Neptune were about to swing into a rare single-file arc. This alignment meant a single spacecraft could visit all four giants in one continuous trip. But the window to launch was strict. If NASA missed the 1977 deadline, they would have to wait exactly 175 years for the planets to line up again. The cosmos forced NASA into a race against the clock. They had to figure out how to conquer the deepest parts of the solar system using 1970s hardware, simply because the universe wouldn't wait. The first major roadblock was distance. Neptune is 4.5 billion kilometers away. Relying on massive tanks of chemical fuel to push a spacecraft that far was a non-starter. The ship would have been too heavy to even leave the launch pad. To bypass the fuel problem, engineers turned to orbital mechanics and a technique called the gravity assist. Instead of flying straight toward their destination, they aimed the spacecraft to dip into the massive gravity well of a planet like Jupiter. It works a lot like a baseball player hitting a fast pitch. By riding into the planet's gravitational pull at a precise angle, the spacecraft steals a tiny fraction of the planet's orbital momentum and slingshots out the other side with a massive boost in velocity without burning a single drop of fuel. Voyager chained these gravity assists together, bouncing from planet to planet, gaining so much speed that it eventually outran the gravitational pull of the Sun. Mastering this maneuver turned the immense gravity of the outer planets from an obstacle into a free, high-speed transit network. Moving through deep space creates a second challenge, staying alive in the dark. By the time a spacecraft reaches Jupiter, sunlight is 25 times weaker than on Earth. Standard solar panels are useless out here. To survive, engineers built the RTG, a radioisotope thermoelectric generator. Inside this device, heavy atoms of plutonium-238 naturally break apart. Just like rubbing your cold hands together creates friction, this atomic decay generates continuous heat. The RTG captures that heat and channels it into electricity, providing a steady power source that doesn't need a single ray of sunlight. By harnessing the natural decay of radioactive elements, engineers built a self-sustaining power plant that thrives in the darkest voids of the solar system. Even with power, Voyager still has to send its data billions of miles back to Earth, and it has to do it using only 23 watts of transmission power. That is less energy than the small light bulb inside your refrigerator. To catch a signal that faint, a whisper that takes 22 hours to reach us, NASA constructed the Deep Space Network. These massive 70-meter-wide antenna dishes on Earth are required to detect those 23 watts from across the solar system. But engineers knew the radio wouldn't last forever. As a backup plan, they attached a golden record to the probe. This gold-plated copper disc is etched with scientific diagrams and carries the audio of Earth's languages, music, and nature. NASA engineered a communication system that beams our scientific data homeward today, while providing a physical record of our existence that will drift through the stars long after the radio fails. The payoff for this engineering came in March 1979, when this 825-kilogram metal box finally arrived at Jupiter, a gas giant large enough to hold 1,300 Earths. Voyager immediately captured the scale of the Great Red Spot. This swirling vortex of gas has been raging for at least 350 years, largely because Jupiter has no solid ground to break the storm apart. But the real shot came when the spacecraft turned its cameras towards Jupiter's moons. On the moon Io, scientists saw active, violently erupting volcanoes, the first active volcanoes ever discovered beyond Earth. Those eruptions are caused by tidal heating. Jupiter's immense gravity is so strong that it physically squishes and stretches Io as it orbits. All that constant rhythmic compression generates internal friction, melting the moon's rock into magma. Then, Voyager looked at the moon Europa. It found a world covered entirely in a thick shell of ice, scarred by deep spreading crack patterns. Those cracks are driven by the same tidal heating. The friction inside Europa generates enough warmth to keep a vast liquid water ocean sloshing around right beneath that frozen crust. This discovery proved that liquid water could persist billions of miles from the sun's warmth. It established Europa as a primary candidate in the search for alien life, and remains one of our top priorities for space exploration today. Eventually, the engineering has to yield to physics. The plutonium core inside Voyager is decaying further every day. To conserve the dwindling power, NASA has been forced to slowly turn off the probe's remaining instruments. Current estimates tell us that sometime between 2028 and 2030, the power will fail completely, and Voyager will go permanently silent. But while its voice will soon die, Voyager's physical journey didn't end at Jupiter. It used that massive gravity well to slingshot itself even faster towards Saturn, Uranus, and Neptune. We'll cover exactly what it found out there in Part 2.